Howdy, folks. Today we're going to go ahead and talk more about the cardiovascular system. Specifically, we're going to talk about how the cardiovascular system, pulmonary system are going to be upregulated and downregulated, both acutely when it comes to exercise, and then how it's going to chronically change. So acutely means when we're actually doing the exercise. So you're going for a run, you're lifting weights, you're playing a sport. What's going to happen? Well, we're going to increase blood flow to our working muscles. Our heart is going to work a little bit differently than it normally does, and that is going to go beat faster. It's going to pump more blood per beat. Stroke volume is going to go up, and when we combine the heart rate and the stroke volume, we get our cardiac output. That's going to go up. Blood pressure on the systolic side, so like how heart is contracting at the top, is going to be higher. Diastolic might go up also, especially for resistance training. It will definitely go up. But if we're just doing some cardio, it might stay the same. Might even go down depending on the position we're in, the intensity we're training at, and otherwise. We're going to have better blood flow to those muscles, and then we're going to get a little bit better blood flow throughout the body in general. And then how we're going to have changes to the blood. Because it turns out we're probably going to be sweating, so our blood is actually going to become more concentrated because we're going to be losing plasma, specifically the water fraction of it, and some of those electrolytes. So in turn, we've got a greater proportion of foreign elements, which in turn is going to make our blood a little bit more viscous, and our blood's a little bit more viscous. Our heart's going to have to work a little bit harder per beat to get that blood out of there. So our stroke volume is going to go down, our heart rate's going to go up, and that gives us cardiovascular drift. And my bad joke, but I will always stand by it, is when in doubt, guys, cardiovascular drift, think about the worst film in the Fast and the Furious franchise, which is obviously number 3. Anyone that says otherwise, never listen to them, they cannot be trusted. So when we're just hanging out, we've got our wonderful resting heart rate. Now, as we get to be in better shape, now this is a chronic adaptation, so it's not going to happen because you did one workout, but we're going to see our resting heart rate is going to go down. That is normal. That's a good thing, because what's happening is we're going to have increased amounts of stroke volume. We're going to have higher amounts of parasympathetic nervous system innervation, which in turn is going to allow it to go lower. Now, it might be up higher because we're in a hot environment, so we're sweating and we're a little dehydrated. It's also going to be higher for things like altitude, because remember that partial pressure of oxygen is lower. Now, our heart rate is going to go up when we think we're going to go exercise. So if you know you're going to get up and about to do something, like before the gun goes off for track and field, if we had a heart rate monitor on all those athletes, we'd see that heart rate going up. And that's because of the sympathetic nervous system dropping in that epinephrine and norepinephrine, along with a diminished amount of parasympathetic tone from our vagal nerve. So our heart rate is pretty much going to go up with a perfect relationship to how intense our exercise is outside of that epinephrine effect. So if you're just scared for your life, your heart rate is going to spike really high. But if you're doing exercise, it's always going to follow that relationship pretty well. Now, we're going to find that it is something that's going to be pretty reproducible, and that you're going to have that max heart rate. It's just going to be stuck there. It's going to go down as we get older in general. And there's a number of different formulas you can use. We use the 220 minus rate just because it's very easy to do, but it's all of them have error values, meaning plus or minus 10%. So you might have someone that's able to go and literally be 20 years old and hit a max heart rate of 220 beats per minute. Another athlete that might only be able to hit a max heart rate of 180 beats per minute, because it turns out they're not able to get up to that level of intensity. And there's a number of other formulas that you can use, but just remember, heart rate goes up when exercise becomes more difficult. And we're going to find that whenever you hit a consistent amount of exercise or intensity, our heart rate is just going to stay at that level. And that's where, if you look at the Submax lab, which you guys are more than welcome to do if you've got access to the treadmill. Otherwise, you can just use the example that I've got, use those values for your lab. That's fine. Now, we're going to see that as our intensity goes up, the heart rate's going to match. And as we get to be in better and better condition, our heart rate is going to actually go lower at the same given stage. Now, this steady state heart rate, that's the basis of what we're using, that relationship for getting that predicted VO2 max based upon what we think the heart rate max is going to be, and based upon what was their actual heart rate at a given work output whenever they're walking on a treadmill or riding on a bike. So this is a good way that we can do this stuff at home and not have to max people out. Because max tests are awesome when we're working with athletes. Working with an athlete, you probably want to know their max, or at least have a really good idea of it, because you're going to find the submax labs can be really inaccurate, especially if you're doing with somebody who's very in really good shape, because they're never really getting up to even a decent percentage of their max. But if you're working with gams and grandpa, you don't want to redline their body, because it turns out their body's not really in shape to be redlined anymore. They're just, when you're getting older, it's just not as good of it's not as safe a decision to do. Now, we have our stroke volume, which is how much blood we're going to pump per beat. Our stroke volume tends to top out somewhere between 40 and 60% of our VO2 max. Now, this is why we need to get heart rate up to a certain level when the submax testing, because your heart rate, yes, is going up linearly, but notice you get this plateau effect of stroke volume. So if you don't go up high enough on your heart rate to where the stroke volume is no longer increasing, you actually are going to be making a mistake, because at that point, you're not having that linear relationship between heart rate and VO2 max. Instead, you're missing this value of stroke volume because you're not testing for it. Now, really, really high level athletes might not hit that peak stroke volume until even higher percentage of their max. But here's some really cool things. If you're dealing with an older individual, a really deconditioned person, if you can get their heart rate up to 40 to 60% of what their VO2 max is, it's probably having positive effects on helping increase that maximal stroke volume. So that's a good thing, in that we're going to find that most people's stroke volume can only double from what it's at rest to max, or heart rate, some people can even go over 4 times increasing their heart rate from where it's at rest to max. So it gives you an idea of how much we're able to really increase that cardiac output. So when you're at the highest level of exercise, your stroke volume is actually going to go down because you don't have enough time for your heart to fill. And if you're doing something like riding a bike or laying down swimming, you actually have a higher stroke volume because you don't have to work against gravity. But when I'm standing up like I am right now, I'm actually going to have a slightly lower stroke volume than if I was to be leaned over, because my heart doesn't also have to pick itself up while it's pushing all that force to eject that blood out of my heart with each beat. So there's a number of things that are going to effectively be able to enhance our heart's performance. And first, we have the preload. So it's how well are we loading the heart in the first place. Now, if you think back to chapter 1, where we have that optimal amount of cross bridges, where we produce the greatest amount of active force in a muscle, which is usually the midpoint. Well, your heart at rest, if we think about your heart like your bicep, it's only working in a small percentage of what it's capable of. But as we allow it to fill more and more, we get it to the point where it's getting that optimal cross bridging. We're never really trying to overstretch our heart in a healthy heart, but we are going to make that heart then go and get to a better position where it's able to contract with more force. Now, if we then drop some stress hormones, our catecholamines in the system, we're going to see that we're going to be jacking up the amount of force the heart's going to contract with. And if we're able to vasodilate and decrease the blood pressure on the other side, the resistance, we're going to have less afterload. So increased preload, increased contractility, decreased afterload, those 3 powers combined are going to massively increase our stroke volume. So if you look at the images on the bottom, you can see the difference in that end diastolic volume and end systolic volume as we're going with individuals from rest to low, intermediate, and peak exercise. And notice the difference between doing it in a laying down and a standing up position, where you're able to actually get a better stroke volume when you're in that you're in that position where you're not having to worry about gravity. So how is this going to be changing during exercise? Well, it turns out we're going to see a greater amount of venous return, which is going to give us a better amount of end diastolic volume, which gives us that better preload when we happen to be exercising. Now, once we get up all the way up to really high, like 80 or 90 and above % of our maximal heart rate, we've got a lot less time for the heart to fill. So we're actually going to have slightly decreased end diastolic volume, which means in turn, we're going to have lower stroke volume. That's why at maximal performances, we actually lose a little bit of efficiency in our cardiovascular system. We're going to have higher contractility because we're going to have all those wonderful catecholamines being dropped in, telling us to get the heck after it. And we're going to have a certain amount of afterload vasodilation, especially when we become more and more well-trained, so the body is even better at vasodilating, specifically to where we need it. So we're going to be able to increase that stroke volume. So notice when we look on the right, the difference between the trained and the untrained individual with when it comes to their maximal heart rate. Notice the maximal heart rates are ending at about the same time, but obviously the cardiac output is way higher in your elite level athlete. Then you look down and you look at, wow, the stroke volume of someone that's in really, really good shape can literally be twice that of the stroke volume of someone that happens to be completely untrained, much less even someone that's even mildly trained. Now, when we multiply our heart rate, so that's beats per minute, multiplied by our stroke volume, milliliters of blood per beat, that gives us milliliters times beat over beats. So we can just go milliliters per minute because we multiply everything together. Yay, math! And from there, we're going to have the total amount of blood we're going to be pumping around the body in a minute. Now, turns out increasing our cardiac output as we increase our intensity, and then it's going to hit the top of its capability when you get to your VO2 max. You are maxed when you're maxed. And we're going to see that individuals, most of us are at about 5 liters per minute when we're at rest. We're just cycling all the blood in our body once per minute. Now, as we go and start exercising, this can be anywhere from 4 to 8x higher than how much we are at rest. And it's going to be a big function of how big we are and how fit we are. So if my goal was to become a better aerobic athlete, one of the first things that I really needed to do is lose weight. Because if I'm a lighter human, but I maintain the same cardiac output of my heart, that cardiac output, what we're looking for with aerobic performance, remember, it's that milliliters of oxygen per kilogram of body mass per minute. Decrease the kilogram of body mass per minute, keep the oxygen content the same, I'm going to be a better athlete for it. But that obviously isn't going to work for all athletes. If you're already a relatively small, slight individual, you can't really hemorrhage any more weight to get yourself more efficient. Instead, we're going to try to increase the performance of your cardiovascular system. And another thing that we need to really keep in mind, guys, which is how much oxygen are we really able to take out of the blood in those areas. And that's going to be based upon what's known as the Fick Principle. Now, the Fick Principle is where the rubber meets the road. So now we have literally that cardiac output, that's the Q, multiplied by our AVO2 difference. How much oxygen were we actually able to extract from the blood as it went around those capillaries? So if we know how much oxygen we actually used, and we know how much, essentially per milliliter of blood, then we know how many milliliters, well in this case, liters of blood we sent around the body, we can figure out the true volume of oxygen we're metabolizing. And that's what we're really looking at. Now, if you look at the graphs on the bottom, we can see that relationship between heart rate as it's going to be at the lowest when you're laying down and the highest when you're obviously running. And you can see how stroke volume is actually kind of interesting. It's higher when you're laying down as opposed to when you're sitting or standing. But then once you start moving, the stroke volume is going to start to go up again. But definitely when you start doing some exercise, the stroke volume is going to be going up even higher. Now, how's our blood pressure going to respond? In the acute sense, we're going to have an increase in systolic blood pressure because our heart is pumping harder in order to get that blood out of it. And then our diastolic is going to stay the same, might go up a little bit, might stay the same. It's one of those things where it shouldn't really be affected too much when we're talking aerobic exercise. Now, if you're squatting heavy weight or deadlifting, your blood pressure is cranking through the roof because you're increasing not just your systolic blood pressure, but your diastolic blood pressure thanks to the wonderful Valsalva maneuver. Now, your mean arterial pressure is equal to that wonderful cardiac output times our total peripheral resistance. So, like anything else, we've got the cardiac output going up, the TPR going down, so we should hopefully do a much better job of sending blood to the areas we need. Now, another concept to keep in mind is what's known as the rate pressure product, and that's going to be our heart rate multiplied by our systolic blood pressure. This is going to literally give us an idea of how much pressure style work the heart is doing, which is what we're going to see a lot more in resistance training, where aerobic training is more volume-based work, where the heart's pumping a greater volume of blood for the amount of work it's doing in order to get that blood around the body. Now, like I said before, the resistance exercise, things can go up. Yeah, it can get even higher than that, though it's not fun because they have to use pressure transducers that are either nasally or rectally, so that's not a great time. And then on top of that, you're already having to lift pretty heavy. But we have some examples there. You're going to see how that blood pressure is going to change depending on what part of the body we're using for the exercise and then the intensity of the exercise being performed at. So what's going on with actually our blood flow as far as how it's being redistributed? Well, it turns out we're trying to send the blood only to where it actually needs to go. We're not trying to send it to a lot of areas that don't need it. So the lion's share of the increase in each level is always going to go to those exercising muscles. And we're going to have, thanks to epinephrine, a vasoconstriction to all the areas of the body that are not as important. And that's going to be, when we talk about splenic circulation, you're really talking about your digestive tract and the organs related to it, along with our kidneys. So I really like these graphs here because you can see, yes, you're going to have local vasodilation thanks to all those things that we talked about, nitric oxide, waste products, and a little bit of other signaling molecules that are going to cause local signals. And then you've got the mechanical vasoconstriction and vasodilation from muscles contracting and relaxing. But you're always going to override the sympathetic vasoconstriction from those local effects, which means your muscles are always going to make sure there's more blood flow going to them. However, you're going to actually get far, far less blood flow to your digestive tract, to other areas of the body. And here's the other thing that's really important to keep in mind is as we get up to those highest levels, so maximal exercise, the amount of blood flow going to our skin actually decreases. And because it decreases, now we're going to have a greater issue with thermoregulation. Initially, once we start exercising, our blood flow, both in percentage and absolute volume, which absolute volume is really what's important here, is going to go up. It's at maximal exercise that is all being shunted effectively to the muscles, and then we're running ourselves into issues. So the graph on the left is based upon absolute. Notice when you look across there, the green bar, which is the heart, stays the same. It always gets the same percentage of blood flow no matter what's going on. Whereas, notice the red, which is effectively your digestive tract with your kidneys, is constantly going down. The orange, which is your brain, is for the most part, is constantly going down. And then notice the skin, it goes up and then it comes back down at the very end, and then muscle is just increasing. But now what we really look at is the one in the bottom right, which is the absolute. And that notice the absolute blood volume to the brain, that orange bar stays the same size the entire time. We need to fuel the nervous system. It turns out that's what's helping the muscles do their job in a coordinated fashion. So that needs to be supplied. We are consistently having lower and lower blood flow to our GI. Our heart is actually absolute sense getting more and more blood flow because it needs that 5% to keep itself going. And now look at the amount going to the muscle, and then once again, how your skin is going to decrease. And thanks to having lower or more blood flow going to your skin, you're going to be sweating out a certain amount of fluid. As you're sweating out that fluid, your blood is going to become more viscous. As your blood's more viscous, you're going to have less of it loading your heart with that preload and return, which in turn is going to cause your straight volume to go down, which means your heart rate has to go up if we maintain the exact same exercise output. That's cardiovascular drift. Look at your graph on the right, and you're going to see how that relationship of cardiac output stays about the same. It has to, because in this example, the individual is maintaining the same exercise output for 50 minutes. But that heart rate is going to go up almost 20% because that stroke volume has gone down considerably thanks to the effects of literally sweating out that fluid. And so our body is constantly trying to send the right amount of blood flow to whatever tissues have that demand. So it's not trying to send more than you ever need to a given system, because it turns out that's wasting resources. And it's obviously trying to avoid ever not sending enough, because if your tissues go hypoxic, especially for too long, they die. So exercise and all your other demands are going to be competing for that limited cardiac output. So hence, if you try to eat a big meal and then go for a hard run, well, now you need that blood flow going to your digestive tract to digest that meal, but at the same time, your body doesn't realize whether you're working out because you just like to, or because you're about to be eaten by an animal. It just knows, well, there's a huge amount of demands. We're going to prioritize the muscles over the GI. The GI is not going to be happy about that, and then you're going to cramp up and possibly vomit. So all of these demands are going to split themselves accordingly. That's why exercise in the heat is so much harder for a lot of people, because you have the increased demands to the skin to cause you to sweat, to thermoregulate, and then you have the increased demands to the muscles in order to keep you exercising. So what's going on when it comes to our oxygen levels? Well, just remember, guys, we have that AVO2 difference. We're going to find that as we get up to higher and higher intensities, we're going to do a much better job of pulling out that oxygen. And notice, guys, it's mixed venous content. So when we're sending this blood around the body, right now, every single tissue in your body is getting at least a little bit of blood flow. Now, for you guys, if you're sitting down, you're hanging out when you're watching this, you're going to be getting most of that blood flow is going to your digestive tract, followed by your brain. You still have 5% going to your heart. You'll have a certain amount going to your muscles, depending on how much you're fidgeting. You got a little bit going to your bones. Every system in your body is getting at least a little bit of blood, but they're not really having to pull out all that oxygen. Now, as we go up higher and higher with intensity, notice how it says mixed venous content in the graph on the right. Because as we're going to go ahead and pull out more and more of the oxygen from the muscles, because they're having such a high demand, when that blood mixes again with all the blood going again to all those regions of the body, just not as much, thanks to the vasoconstriction to it, we're going to still have a lower, but never notice a net zero amount of oxygen still in the blood when it's returning to the vena cava, because it's all mixing as it goes through our body. Now, we're going to have that plasma volume that's going to change, thanks to the wonders of our electrolytes. Now, when we talk about fluid movement, and that's going to be into and out of tissues, we have hydrostatic pressure, oncotic, and osmotic pressures. So think back to chemistry, your biology of we have so many solutes in solution, so many in the cells next to it. It's going to pull water in from one to the other. And some of you guys maybe naturally felt this phenomenon or observed it when you worked out hard and you did like a high carb meal, but not a lot of water to go with it. You pull a lot of muscle or a lot of glucose, which is then turning glycogen in your muscles, which in turn is going to pull a lot of water out of your bloodstream and sometimes your interstitial fluid. So that way it's going to fill up your muscles. What bodybuilders do to give themselves a drier look, a leaner look whenever they're obviously trying to get ready for competition. And the opposite is true, especially for females, depending on what part of the cycle they're on, where they're going to have greater amount of fluid retention in certain parts of their body. So this is completely normal. Now, as we're standing upright, well, it turns out our plasma volume, because of gravity, is naturally pulling more of it into the lower body, along with we're going to have the effects of changing with pressure from vasodilation, vasoconstriction, metabolites that we're producing, and the wonders of losing fluids thanks to sweating. And as we're losing these fluids, we are once again getting hemoconcentration. So we're literally starting to increase the effective concentration of blood cell, which is a good thing because technically we can carry a little bit more oxygen per unit of blood going around the body. Remember, it doesn't have as much time because it's being pumped around a lot faster. And then secondarily, we have the issues now we're not able to pump as much per beat through stroke volume. So either way, our heart is having to work harder. Now, how are we going to regulate this? Well, it turns out we're getting information from a lot of different areas in the body. So from different chemoreceptors and mechanoreceptors, it's telling us we need to increase our heart rate or decrease our heart rate. And this response time is literally within 1 second of when we really start exercising. Or we still have that as anticipatory because from our own nervous system, we're like, hey, this is coming, I need to be ready for it. And because of that, we're going to have that changes in our heart rate, changes in our blood pressure. And thanks to the baroreceptors, we're going to vasoconstrict and vasodilate to make sure that we're going to keep ourselves safe. And that's where that increased blood pressure from resistance training, you guys have maybe seen somebody black out from lifting really heavy weights, or you maybe have had a moment with yourself, you kind of saw stars. That's a great example of those baroreceptors did a good job of vasoconstricting, so you're not sending too much pressure of blood to the brain and possibly causing an aneurysm, but then they didn't relax fast enough afterwards, and because of that, you then effectively have a moment where you're choking yourself out to your own brain, and you can go to night-night if you're not careful. Now, all of this is being integrated by a number of different systems as we go throughout the body. Remember, we're trying to make sure that we maintain our blood pressure, so we're getting that blood flow appropriately everywhere, not too high, not too low, and then we're going to start worrying about making sure that we're prioritizing whatever tissues need more blood flow than the other. So the brain is, remember, always taking about the same amount of absolute total blood flow. The heart is always taking the same relative amount of blood flow. But from there, how much more can we shunt towards muscles? How much more can we shunt towards the skin? And then how much can we shunt away from our digestive tract and otherwise? So do yourself a favor, slide 20 of what we got in here. Look at the slide. Make sure you understand this flow chart of how the body is actually going to be controlling these things and really making sure that we're regulating blood flow appropriately when you are exercising. Now, we're going to be breathing faster, okay? We're going to be taking bigger breaths and we're going to be breathing at a faster rate. And then we're going to hit a second phase of increased ventilation, and this is called the ventilatory threshold. And this is when your breathing goes really fast, where you're not really able to hold a conversation with the next to you. And that usually comes right before you have the accumulation of blood lactate, because we're trying to make a greater amount of bicarbonate to help buffer the effects of that wonderful proton that comes with it. And that's going to be a really good indicator for you as a coach of when you know your athlete is going into utilizing anaerobic metabolism. And if someone's getting into better and better shape, that's going to be at a higher and higher percentage of their VO2 max. So we're going to see that our ventilation tends to increase based upon whatever the needs are for the muscle. So if we're working out really hard, we're going to be breathing a lot harder. If we're not working out as hard, we're not going to be breathing as fast. It makes absolute sense. But what we're also going to have is a delayed recovery, and that's going to be related to what's sometimes referred to as EPOC, which we talked about before, which is because of that oxygen debt. It's going to take you a little bit of time to get your breathing rate back to normal, so that way your body can be at rest and allowing yourself to recover to a much greater ability. And that's going to be based upon, once again, returning yourself to homeostasis, bringing lactate down, replenishing ATP, allowing your tissues to be fully oxygenated again, to where now the body is back to normal. Now, there's a couple of irregularities you can have, like dyspnea, where you can talk about shortness of breath. This can happen to a number of individuals, which usually it's individuals that aren't in very good shape. And literally the respiratory muscles are not in good enough condition to work at those higher intensities. You can have hyperventilation. This is someone that's got probably maybe a little more anxiety, where they're breathing really fast and really big. This is going to cause a greater amount of pressure or amount of CO2 to be removed from the bloodstream, which in turn can cause an increase in blood pressure, which is going to then give you a lower interest in breathing, or not interest, drive to breathe, so you don't have to breathe at as high of a rate. And this can actually be potentially useful if you're doing things like really high repetition work or really hard anaerobic testing to give you a slight potential advantage. Now, the Valsalva maneuver is going to be bearing down while closing the glottis, which is going to give us that fluid ball advantage where it's going to build a greater amount of pressure in our stomach, which if we think of our rib cage as kind of this bony structure that, I mean, it has a certain amount of flexibility and mobility, but it's relatively rigid. We have our hip bones, which are very rigid. And then in between the two, we have a slinky. And then slinky is our lumbar spine, which is obviously supported by a variety of different muscles from our spinal rectors to our obliques to our rectus abdominis or transverse abdominis. But by bearing down and holding that breath, we're now able to use our own diaphragm and otherwise to help enhance that pressure, which in turn is going to decrease your risk of injuring yourself, specifically when you're doing heavy lifting. But if you're working with an older individual, someone who has cardiovascular problems, you don't want them to be doing the Valsalva maneuver. You want them to make sure they're going to be safe. It's something to build up to, but at the same time, if you're working with young folks, you don't really have to be too worried about it. Now, we're going to see that, once again, as we're going to go ahead and increase our effort, we're going to have that point where the ventilation increases even faster than it was before. And that is that ventilatory threshold. And this is, once again, a really good indicator of when someone's starting to have to utilize anaerobic metabolism to keep up their work output. So the basic idea is once we start using anaerobic metabolism, it means we're tapping into another fuel source, which can be good because now we're starting to tap into some of those bigger, more powerful type 2 fibers, or the fibers obviously aren't able to get oxygen at the rate of which they're able to still maintain that output without going anaerobically, but we're going to have the metabolite accumulation, which means we're going to have only be able to work above that intensity for a finite period of time. And it's also going to be stuff that's a lot higher stress on the body is anaerobic style work, specifically lactic anaerobic work, whereas it's relatively easy to recover from low intensity or moderate intensity aerobic style work, especially when we're controlling the amount of impacts we're having. So if you're working with someone, you're trying to get them in better shape and you want them to be able to do it in a way that's approachable, there's nothing wrong with going for a walk and just having a conversation with them. And as soon as they're no longer able to keep up their side of the conversation with you, you're going at too high of an intensity for their aerobic system, back it down a little bit because they're still going to get a training effect, but it's going to be a lot more comfortable for them and make it a lot easier for them to maintain that. Now, it is not the same thing as your lactate threshold. It just happens to be a relatively decent indicator. Now, the better way to go about this is to look at the total amount of oxygen and CO2 that we're taking in and seeing that point of which where we're going to have a greater amount or a lesser amount of oxygen that's being taken away per breath for the amount of total ventilation, or we're looking at that respiratory exchange ratio is definitely getting over 1. Now, there's a number of possible limitations. It's rare that you're going to have an issue with literally you're not able to breathe enough to keep up your exercise, but obviously individuals that are going to have issues with asthma or otherwise can be an issue, and if you happen to be up at altitude. But we're going to see in reality that some of our super high level athletes, they're potentially not going to have the issue there because they're literally not able to breathe at a high enough rate for literally how much the cardiac output can be and then how much oxygen they're able to take out of each breath. Now, remember guys, we do want to maintain our pH within certain ranges. The muscle can handle a lower pH than the blood, but once we get too low in either, we're going to have literally a dysregulation of the enzymes related to energy production. So it doesn't matter how hard we want to work, we're not going to be able to keep it up. And that's going to be what's literally going to effectively eventually occur thanks to all of that anaerobic metabolism we have going on and that accumulation that's going to slowly occur inside of the blood. Now, you can get it really rapidly if you do things like that Wingate test where you're just going hard in the paint, giant amount of lactate production. You're not going to be able to keep that up. And feel free to please laugh at the fact that I had to do 2 of them because that was awful, but I now think that's funny. It just took me, a little bit. Now, if you're going to work with your other athletes, you're going to find that you hit a point where it's like, okay, we're really going to maybe hit that fatigue 10 minutes on the road, but you still want them to be able to keep it up for a long enough period of time that they're going to get a decent training effect. Now, Here are some ways that we're going to be able to make a buffer. Now, bicarbonate is doing most of the work. Hemoglobin is also going to be buffering a little bit, along with general proteins like albumins, and then phosphate we're going to have in the blood. A buffer is something that's able to take one of those protons and bind it to itself so it's not free floating. So it's not able to drop the pH because it's bound up. That's what buffers effectively do. And we want to have enough of these ability here so we're going to be able to get that pH where it needs to be. And if we're doing active recovery, meaning doing aerobic, very low intensity work, we're going to be able to recover from this anaerobic work a lot faster and get that lactate down. So that's why doing aerobic recovery, as much as it might annoy the heck out of you when your coach said, go for a slow jog, go for a slow swim after doing hard work, is actually the better way to clear lactate, which in turn is going to allow you to perform at a higher level because you're using those aerobic cells to use lactate as a preferred fuel, which is also going to pull out those protons and utilize them for effectively what's being turned into water. And turns out exercising around pollution is bad. Carbon monoxide is hecka bad. It binds really well to hemoglobin, better than oxygen, which is going to naturally lower the amount of oxygen you can use. So please don't work out around industrial machinery inside of enclosed spaces or a car that's running inside of a garage with the door shut. Bad, bad, bad. Along with issues with ozone and sulfur oxide, which are things that are going to naturally be produced through things like the wonders of high amounts of electricity used by some piece of equipment, along with car exhaust and otherwise. So if we really want to perform well aerobically, we have to do it with cleaner air. And obviously that means trying to work out in hopefully areas that aren't around massive highways or roadways or a lot of traffic. So thanks for listening, guys. Stay safe out there and have a great day. If you have any questions, comments, as always, leave them on here or email me directly.